going to. Tim is the director of the Global Systems Initiative, and he's chair in Climate Change and Earth System Science at the University of Exeter. He's also a member of Future Earth Commission. Among many diverse research interests, Tim has been a pioneer in the study of tipping points and tipping elements in the Earth system. I join our audience in looking forward to his talk entitled Learning from Past Climate Tipping Points to Avoid Future Ones. Thank you very much, Tim.
Thank you, Mike, for the kind introduction. Let me just share my screen, folks. Sorry I couldn't be with you all in person. I trust you're seeing that all okay. Yeah.
Yes, good.
Great. So yeah, what can we learn from past climate tipping points to avoid future ones? Well, I'm going to start with a little toy model, a movie of a system that I'm pushing slowly past a tip towards and eventually past a tipping point. And like many complex systems, it has alternative stable states. It can only ever be in one of them, but the one it started in is losing stability thanks to the forcing. And at some point, just there on my computer, it tipped into the other stable state. And when that happens, it's because whatever damping feedbacks were maintaining stability, well, they've got weaker, and some amplifying feedbacks that propel change have taken over the dynamics at the tipping point. Now, lots of systems we now know can exhibit tipping points across different kind of time scales on the x-axis and space scales of system. I'm going to dwell somewhat on parts of the climate or the Earth system, the things I've coloured in gold, but I'll also touch on abrupt changes and tipping points in ecosystems, and aquatic ones are coloured in blue here, terrestrial ones in green, ones at the land-water interface in grey. And then, of course, there are our social systems in red. They've shown some past tipping points. We'll come back to those at the end. And then there's the nasty one in the middle, civilization collapse, that we need to try and avoid happening again. So I'll start on the climate tipping points. Something I've been working on for nearly 20 years, trying to identify which big scale bits of the climate system could pass a tipping point, particularly under human activities and anthropogenic climate forcing, as it's called, this century. Plus, on this map, the Antarctic ozone hole that we already tipped late last century and we're busy trying to repair. Well, when we drew up this original map, we had several sources of evidence to try to identify the elements of the climate system that might be pushed past a tipping point. And I would say the most fundamental or key piece of evidence really was the paleo record. It was the record of past abrupt climate changes that first woke, I suppose, the scientific community up to the possibility of tipping points. So famously, well, that includes many things, probably including tipping into the ice age cycles, tipping of the frequency of the ice age cycles, but then within the last ice age cycle, this famous evidence of multiple abrupt climate changes, the so-called Dansgaard-Oeschger events, associated with kind of tipping points between different states of the Atlantic Oceans, overturning circulation, somehow coupled to Arctic sea ice cover, somehow coupled to changes in the atmospheric circulation as well, and manifesting it with implications around the planet, as we'll see a bit later. But if we just zoom in to the last 30,000 years of that record, and these are two different Greenland ice core records, we begin to see, as well as resolving what's going on with these Dansgaard-Oeschger events, we see the number one is also known as the Bolling-Alerod onset of warming abruptly, and then there follows an abrupt change after the Younger Dryas cooling into the entry into the Holocene, and some subsequent shifts that don't look as big on this scale, but were quite profound. And I'll maybe touch on a few of those, including the onset of the end of the African humid period, or browning of the Sahara, as it's sometimes known. So yeah, the paleo record gives us some big clues about which bits of the Earth system can be tipped. But so hopefully do our climate models. So if we look in existing climate models and future projections, it turns out that there are quite a lot of abrupt shifts going on, at least at local or regional scales. And interestingly, when you plot those abrupt shifts happening in different models as a function of global warming above the pre-industrial level, you find the alarming result that they cluster at quite low levels of warming, 1 to 1.5 degrees, the range we're in now, 1.5 to 2 degrees of global warming. There'd be lots more abrupt shifts at high levels of warming as well. There just aren't many scenarios going up there. And on the map, you see where are these abrupt shifts happening in different climate models. And that starts to give us clues to tipping elements that weren't on my original map, like the subpolar gyre up here, which also abrupt shifts in that are associated with, for example, the Little Ice Age. However, we know that our climate models are kind of more stable than reality in some sense, because they famously or infamously generally fail to be able to reproduce past abrupt climate changes. And only recently has there been significant progress from some groups in being able to simulate some iconic abrupt climate changes. So this is work by Peter Hopcroft and Paul Valdez, where they were able, through some clever tuning of the Hadley Center's HADSI M3 model, to get it to be able to reproduce the past kind of what's colloquially called Green Sahara, capture abrupt declines in rainfall over North Africa, and get the timing of the drying of the Sahara region approximately right compared to where it happens in paleo reconstructions, as well as the magnitude of the change. But that was a real success story, because that has been a persistently hard problem for models to solve, if you like, for some decades. And still models are struggling to reproduce other abrupt past climate changes. So that probably tells us that we've underestimated the likelihood of abrupt changes from models in the future. And that means we're also turning to observational evidence now for the telltale signs that bits of the climate, the tipping elements previously identified, are already showing signs of destabilizing. So I've summarized a bunch of that recent observational evidence on this map. I won't go over it all, but not only is there direct observational evidence for example, destabilization of a key part of the West Antarctic ice sheet and a key marine grounded basins of the East Antarctic ice sheet. Again, paleo evidence has been really crucial in reinforcing the sense or the understanding that there have been very striking past abrupt retreats of sort of submarine grounded basins of both the East and West Antarctic ice sheet. So these are things that are starting to appear on a revised map of the tipping points, which I'll come to in a minute. But before I get there, this was a summary of what the Intergovernmental Panel on Climate Change has been assessing to be the risk of crossing climate tipping points as a function of successive assessment reports. 2019 here refers to special report on 1.5 degrees of sea warming in 2018 and the special report on the oceans and cryosphere in 2019. But hopefully you can see the take-home message of the slide already, which is the longer we study abrupt climate changes and tipping points, the bigger we think the risk they pose is, or rather, the closer the tipping points we think are to the present temperature. And of course, all during that time, we've been pushing the temperature up. So now we're at 1.1 or probably more like 1.2 degrees C of global warming. And even by the IPCC's assessment, we're clearly in the danger zone, if you like, with a significant likelihood of passing some climate tipping points. So let's have a look at that in a little more depth. And what I've been involved in with colleagues recently is an attempt to reassess the map or the list of climate tipping elements, pulling together all these latest strands of evidence. And we've decided to subdivide the list or the map into what I'm calling here global core climate tipping elements. That would be things that contribute to the overall mode of operation of the Earth system. that when you tip them, it's on a massive spatial scale, at least 1,000 kilometers, and or they have a global impact, which I define as feeding back to global temperature at least 0.1 degrees C of additional warming. And you see these new entries on the map, like the East Antarctic subglacial basins, and in fact, if you warm enough, the East Antarctic ice sheet. But we also identify some what I'm going to call regional impact climate tipping elements that defined as contributing significantly to human welfare. So if we lose them or tip them, it hurts a lot of people, or they just have great value in themselves as a unique feature of the Earth system. Well, losing tropical coral reefs will hurt a lot of people and their livelihoods. And we also see that example of the Sahel and the West Africa monsoon on this particular map. And what we've been doing is trying to assess that what's our best estimates and uncertainty range on what level of global warming to pass these different tipping points that I've just shown on the two maps. So the ones in the bold font would be ones that are global core tipping elements now, and the normal font would be the regional impact tipping elements. And for each of them, we've given a sort of burning embers temperature range, and the dotted line is our best guess of where the tipping point might be. And the range is defined by, well, the bottom of the range is defined by, well, one model has a tipping point at that temperature level, about 0.8 degrees C of global warming in the case of the Greenland ice sheet. And the model that tips, but at the highest temperature level, marks the upper bound here where the color is dark red. And then we kind of got underneath that, the last ice age and the warming as the ice age to give some kind of sense of temperature change. But we also have up here in the rainbow colors that I'll expand now, the kind of range of IPCC future climate projections this century. And all this detail here, the sort of shaded boxes, well, get your eye in on this line here, the 2.7 degrees C of global warming. That's where we're heading under current climate policies. And unfortunately, that risks triggering a whole bunch of tipping points if our assessment is right. Even in the most optimistic case, all the targets from the latest Conference of the Parties in Glasgow in last November, we'd still be heading to nearly 2 degrees C of warming, and that still risks multiple climate tipping points being triggered. And actually, one can plot out when they might be crossed as a function of time from now. But that should be enough to make the point that we're running a real risk of already of having passed or being very close to passing some climate tipping points. And that was just treating them in isolation. What the paleo record shows us, as we'll see in a minute, is that there's strong evidence that these tipping elements in the climate system causally interact, and sometimes in a bad way, where tipping one thing makes tipping another a bit more likely. And we begin to see that in observations as well, because we have this extraordinary Arctic amplification of global warming, the Arctic warming 2 or 3 times as fast as the global average because of the abrupt retreat of the Arctic sea ice, exposing a dark ocean surface that absorbs a whole lot more sunlight. And that extra Arctic warming is a big contributor to the unprecedented melting that's been going on the Greenland ice sheet, and the abrupt thawing of parts of the permafrost, and burning and pest outbreaks in the boreal forests. And then, well, there's extra warming in the Arctic means extra precipitation, rain or snowfall, and that mixed together with fresh water pouring off the ice sheet are both now seen to be contributing to a general slowdown of the Atlantic's great overturning circulation. And we know from Earth's past that when that slows down, it drags the band of rainfall all around the tropics, the intertropical convergence zone southwards. So that can disrupt monsoons in India, West Africa, in the Amazon, and it leaves heat behind in the Southern Ocean, which is the biggest risk factor really for destabilizing the West Antarctic ice sheet and the bits of the East Antarctic ice sheet grounded well below sea level. So in short, there's a risk of tipping point interactions, and in the worst case, cascading interactions. And this is just one example of paleo data synthesis through the last ice age, just showing correlated changes recorded in Greenland attributed to those abrupt switches in the Atlantic overturning circulation, correlated changes in the North Atlantic region with changes in the monsoon over the Amazon, and also correlated with changes in the monsoon over India, all the way around the planet in India. Yeah, just to illustrate the point I verbalized about the coupling, the global coupling together of tipping elements in the climate system. And the paleo record, of course, gives us beautiful detail now. The harder you all work, it gives us more and more detail on particular abrupt shifts and pulls out, where how the abrupt shifts differ across space and across bits of the system, like the Bolling Alrod warming or onset being sort of picked up in various proxies around the map on the left here, as well as some other abrupt shifts more recently on the right. And looking into the paleo record, one doesn't just see those abrupt shifts in the physical climate system. Now, I think as a community, we're at the point where, as some of those records shows, we're also seeing abrupt shifts in ecosystems in the paleo record. And sometimes we're seeing abrupt shifts in past societies. And we're beginning to get enough resolution and synchronization on our records to be able to see correlation, if not causal interactions, between abrupt shifts in the physical climate system, abrupt shifts in ecological systems, and sometimes abrupt shifts in past social systems. And as in a paper led by Victor Brovkin, as that review explains, you can sort of begin to tease out of the paleo record evidence of these cascading abrupt changes, cascading down scales, if you like, from the global physical climate system through regional ecosystems to local past societies. Now, it's those kind of bad abrupt changes that we really need to avoid in the future. And we would often, I suppose many commentators would argue that, oh, well, everything is profoundly different now and we're much better able to cope with abrupt climate change than past civilizations. But I wouldn't be so totally sure. And this is just to show one study that we did looking at, okay, what would happen if we had a collapse of the Atlantic meridional overturning circulation, during this century? For the sake of argument, we're going to make it collapse fairly quickly, just as a thought experiment. And I'm afraid this is a bit parochial for me coming in from Great Britain, but we're going to look at how that would impact farming and land use in the UK, just one sector of our economy. But we see in this plot A, how parts of the UK has a climate good enough to support arable farming and brown, and part of it, the climate conditions aren't quite good enough for that. So you have a lot of grassland, pasture, livestock raising and green. Without any kind of climate tipping point, climate change already does bad stuff. It produces heat waves in the southeast of England that would stop wheat farming there. But the big story is, if there were a climate tipping point, in this case, the collapse of the Atlantic overturning circulation, wow, it would do extraordinary things for the UK. It would essentially dry the climate so spectacularly that it would eliminate arable farming pretty much from the UK. And farming then would be the least of our worries. We did some calculations. Okay, how much irrigation would you need to try and recover arable farming in the UK? But the numbers are just spectacular. And you conclude that there just wouldn't be enough water from when it rains in the winter locally to support arable farming in the summer. Instead, you need massive adaptation to pipe water from the mountains in the west of the UK where it still rains to the rest of the country. And yeah, growing food would probably be the least of our worries, because we'd have a massive water crisis on our hands in the southeast of the UK. So lots of bad things, unfortunately, might be coming our way, but we're not quite sure how close the bad tipping points are. And we know our models are imperfect, so our forecast capability is not perfect. So it's a bit metaphorically like being in a boat, maybe an open canoe, hopefully with a paddle, hopefully with a few friends who can help paddling, but we're sort of drifting downstream. We can hear this really loud rumbling noise ahead and the possibility of a dangerous tipping point. If we're going to do anything about that, we need to change course before we get to the tipping point. Otherwise, it's going to be basically too late to act. So yeah, we want some kind of warning, more reliable warning signs of how close really bad tipping points are, so we can start metaphorically paddling hard in the opposite direction. And yeah, models are helping us, paleo data is helping us get a sense on this, but it's also possible to get directly from observational data some early warning signals of whether we're heading towards a tipping point. So here's the same movie as before, but now watch the ball rolling around and see that it rolls around slower before we get to the tipping point. That's because the system is losing resilience in ecologist language. It's basically that the damping feedbacks that resist change are getting weaker and weaker before the tipping point. And that slowing down, so-called critical slowing down of the system before a tipping point, that gives up really general and fairly reliable early warning signals, like the red line at the bottom, which is a measure of how similar is one time point to the next, lag one autocorrelation in time, it's called. And that indicator goes up as everything slows down before a tipping point. And that's detectable in data, as is what should accompany it, which is an increasing variability in the data. In other words, the ball rolls around further for a given nudge just before a tipping point. And there's been lots of work for the last decade or so trying to check whether such early warning signals were present before abrupt climate changes in the past. I might show one of those in a minute, but basically the story is, yep, with lots of caveats as to when it's appropriate to do this and the data requirements. There certainly are cases where there is early warning signal shows up. And now we're looking in observational data to see if we see it. So here is an example in the beautiful richness of remotely sensed data, here looking at the Amazon rainforest and a proxy of biomass fluctuations called vegetation optical depth. And if we see the colors going darker blue, we're seeing that indicator, lag1 autocorrelation in time, going up, the early warning signal going up. To begin with here, we're going through the late 1990s, and actually things are getting more stable. The colors are getting brighter yellow or green. But unfortunately, since the early 2000s, we pick up a strong signal of the Amazon rainforest losing resilience, losing stability, doing this slowing down, consistent with approaching the tipping point. And that's shown here just in the red areas, which are the places, the deeper the red, the places with the strongest slowing down or destabilization signal since the early 2000s. I said, well, these methods have also been tried and tested on paleo data, and they don't always work, and we can have some discussion about, the conditions under which they could work. But there are some encouraging case studies where, for example, looking at really high resolution paleo data from famous cave speleothem records in China before the termination of the penultimate ice age in this case, basically the early warnings, the data show abrupt transitions in the monsoon from these two caves. We kind of cut the data before the final abrupt shift linked to the end of the penultimate ice age. And we see in the data the early warning signals we expect of this rising lag1 autocorrelation and rising variance before the abrupt shift or tipping point. And we see it in both of these cave records. So I think some further work on paleo data is going to, I think, help further refine our early warning capabilities for tipping points, which could be really crucial going into the future, both warning against bad tipping points, but I'm starting to think that we might also be able to see the early warning signals of some good tipping points that we need to see in society if we're going to get on top of the climate crisis. And I'm one of many people now saying that we need to think about the challenge facing us right now as needing to find and trigger some positive tipping points to get out of the business as usual state of the economies powered by fossil fuels and into some kind of alternative decarbonized state of the economy. So just to wrap up, this isn't just a wish or a hope. There's real evidence of positive tipping points starting to happen in nation scale systems like the Norwegian mobility, if you like, or transport system, where what we're showing here is an extraordinary shift from petrol and diesel cars to electric cars over just the last decade in Norway. Also, parochial again, over here in the UK, 10 years ago in 2012, 40% of our power supply was from coal burning. And in the last decade, that's plummeted to almost zero and being replaced largely with renewables, a real tipping point change. So those are exactly the kind of positive tipping points we need to avoid the bad climate tipping points. I'll just wrap up there and just say, well, look, the past is telling us where and when climate tipping points can happen, how they can interact, and how they can cascade, often in a bad way, across climate, ecological, and social systems. Past abrupt change is an absolutely crucial test of our climate models and a great testing ground for tipping point early warning methods. The short version of the current situation is we're in a climate emergency, and we might already have passed some climate tipping points. We're certainly heading close to others. So if we're going to avoid the worst now, we need to find and trigger some positive tipping points to accelerate some transformative change in a good way in our societies to avoid some bad climate-driven tipping point changes. Thanks very much.
Thank you, Tim. I think we have a few minutes for questions that came into the question and answer. I could read them to you.
Great.
Thank you. So the first question is from Andreas Heinemeyer, and it is looking at the Vostok ice core, the CO2 and temperature, it seems like we've already pushed the system.
Yeah.
And so the question is, how can we still think that we haven't reached tipping points yet?
Well, I sympathize. I guess at some fundamental level, we passed a tipping point, possibly in the Industrial Revolution, and certainly in what some people call the Great Acceleration after the 1950s. So yeah, and I'm essentially agreeing with you that we probably have passed some climate tipping points that we're not going to avoid, but I would still argue there's a lot of ones we haven't crossed yet that we still could avoid, and we should do everything in our power to avoid them. But for sure, we're going to have to adapt to some of these tipping point changes, and that poses sometimes a profound challenge because there are limits to adaptation.
Okay, I think you've actually just addressed Marie-France Lutz's question, which was about is our only hope for adaptation. So I'll go on to Paul Butler's question, which is the government listening to you, UK government or otherwise governmental?
Well, I flashed up a few slides at the end on the positive tipping points, and I did that work with Simon Sharp, who at the time, until very recently, was a key part of the UK government cabinet office COP26 team, who was one of the leaders of the negotiations in Glasgow in COP26, and the architect of something called the Breakthrough Agenda, launched at COP26, which commits nations comprising more than 70% of global GDP to a policy agenda to try to deliberately bring forward these positive tipping points. So yeah, I wouldn't say all of government is listening to any of us, but I would say an important part of, in this case, the UK government I've been working closely with to try and kind of bring this thinking into policy decision making.
Okay, next question is from Julien Emilge, and it's that critical slowing down is extremely useful, but few climate series have the properties for it to work. Do you have a general criteria for this?
Yes, absolutely, Julien. So there needs to be what mathematicians call a good separation of timescales for to be confident that the critical slowing down phenomenon is going to show. So you essentially need to know something about the timescale of tipping of your system, and then you need it to be forced slower than that by perhaps an order of magnitude for the system to stay reasonably close to equilibrium. In other words, the ball to stay reasonably close to the bottom of the valley so you can watch it getting nudged around. But then, of course, if you're going to resolve what the ball rolling around is doing, you need to monitor the system about an order of magnitude more frequently than the tipping timescale in order to resolve whether it's slowing down or not. So that sets, as you say, some stringent constraints on the data needed. And you may, also, that may rule quite a few systems out, but not all, in my experience. And of course, the great thing that paleoclimate research can do is potentially reconstruct longer records for slow systems like the Atlantic Ocean overturning or the ice sheets that might eventually give us the right enough data to be able to do early warnings that we can't do now because we don't have enough. We don't meet the data requirements for some of those systems.
Yeah, or we test the ideas with self-similar, much faster systems we can observe in real time.
Exactly.
Okay, Alex Pace asks, what is the relationship between the medieval climate anomaly and tipping points? Did the MCA trigger some tipping points given that some regions were warmer than today from the MCA?
There's a good question. An excellent question as to whether one could argue that it triggered some regional or local tipping points. I mean, my understanding from the proxy compilations is it wasn't globally coherently warmer in the same way as the recent anthropogenic warming signal, but it was still a great question to look where it was regionally warmer, what consequences did it have? I've been concentrating a little more recently on the transition from the medieval climate anomaly to the Little Ice Age. One of our PhD students in Exeter actually has done a really nice analysis of some very high resolution and annual ringed bivalve records from the North Atlantic.
Yeah.
And has some evidence that there is the early warning signals consistent with the possibility that that transition into the Little Ice Age might be of a tipping point type for the subpolar gyre of the North Atlantic, which is something that several groups have suggested from models. So that's a work in progress, but I think that that transition might have tipping point dynamics at the North Atlantic regional scale.
Sounds like there's a possibility of connecting to the social tipping points too.
Absolutely.
Raphael Hebert asks, it is unclear to me what a tipping point in Greenland and Antarctica means. So the timescales to melt such ice sheets are on the order of millennia, whereas the tipping points proposed should be crossed in the coming decades. So how could it be irreversible given that there could be major achievements in CO2 reduction, greenhouse gas reduction in the coming century, well before the ice sheets have melted?
Yeah, well, that's a good question, Raphael, and it's something that various groups are working on, whether it's possible to rescue an ice sheet that's past a tipping point by cooling things down again. So you're right to highlight that of all the bits of the climate system I talked about, the ice sheets are the slowest or the most sluggish. However, they're known to have very strong internal reinforcing feedbacks and hence true tipping points in the sense that mathematicians would call bifurcations. In the case of Greenland, the feedback that's most commonly talked about is how as the ice sheet descends in altitude as it's melting, that warms the surface further, which further pushes the surface mass balance in the wrong direction. Whereas in the marine grounded ice sheets like West Antarctica and parts of East Antarctica, it's partly to do with the topography of the grounding, the bedrock slope that the ice sheet may retreat down, and the fact that the physics is such that once you get on this bedrock slope that's going deeper as the ice sheet shrinks, the physics adjusts in a way that should propel the ice flow faster. So that's self-reinforcing. You ask, can it be rescued? Some toy models suggest, well, maybe if we did some large-scale carbon dioxide removal from the atmosphere or something, maybe we could overshoot the tipping point, then cool things down again and just about recover the situation. But frankly, I think we need to look at that with the state-of-the-art models, not toy models, and that's still a work in progress to find out the answer. It's certainly an important answer because if we can't reverse those tipping points, we might already be committing future generations to say 10 meters of sea level rise 1,000 years or so hence, which is they're not going to thank us for it. I don't know how it will be written about in their history books, but probably not favorably.
Thank you. I think that's all the questions in the question and answer. I'd like to ask one last one that I had as we were going. So you can see tipping points in simple, what you call toy models, and you can see tipping points in very complex models we use for climate change projection. But you also mentioned early on that you typically don't see quite as much evidence in the latter as perhaps you do in the former. And I wonder if you could maybe explain why that might be the case.
Well, as Paul Valdez put it a decade ago, the climate models can tend to be built for stability. I think there's a little bit of sociological reasoning here. So the history of climate modeling, if you go back to the 1990s, is that it was quite hard to get a coupled ocean atmosphere model just to produce something like the current state, for example, of the Atlantic overturning, especially hard without doing what's called flux correction of the models.
Yes.
Often the models would settle into the wrong quote unquote state or some crazy state. So I think what must have happened from knowing the groups involved is there was quite a bit of tuning of the models to get something that looked like reality, get the models in the right basin of attraction in mathematical language. Now that might have inadvertently introduced too much stability in that, at least in that aspect of the model. There's a case to be made for that, because subsequent evidence and process-based understanding suggest their models are biased too stable, some of them for the Atlantic overturning. So yeah, that's a little bit of why there might be a bias towards stability in high resolution climate models. But there's also been some really major progress recently, for example, using remotely sensed data to kind of recalibrate the models in terms of the ice crystal content of the clouds in the models. And that has suddenly made a bunch of the climate models way more sensitive. In fact, you could almost argue prone to some kind of cloud tipping point that doubles their so-called climate sensitivity. So I think we're heading, shall we say, in the right direction scientifically towards state-of-the-art models that are giving a more faithful representation of the possibility of tipping points. But unfortunately, that rather takes us in the wrong direction from the point of view of the risk that these events pose. I'm rather hoping I'm wrong on all of this, but that's where we are.
There's one more question that got finished by Jay Schmidt, and it's the question of aren't anthropogenic measures and human environmental interaction on regional scales not more important in terms of risk to people in many parts of the world? And how can we assess tipping points in land and environmental use compared to climate tipping points? So the question about land use and land surface change. Thank you.
Good question, and we can address that obviously again through data. If we can get good data on those relevant ecological and social coupled systems, we also, those of us who deal with theory and models, obviously have to think fundamentally about whether the nature of the system changes once you see humans as an absolutely integral part of it, potentially changing their actions and their decisions all the time in response to the system. But there's quite a body of work now from what in ecology got called the Resilience Alliance, a sort of collective, if you like, of researchers who've built up a whole catalogue of these recent abrupt shifts in social ecological systems, as they call them. I believe the paleo record is giving us ever more great examples of those as well. And yeah, we start with the big data revolution to get enough data from contemporary social ecological systems to be able to apply some of the same kinds of methods of looking for early warning signals of abrupt shifts and potentially building process-based models even of the systems, although we're not quite there to the same degree we are with the climate. But what has struck me is that even some analysis of where good data, archaeological data now is available for past societies, including, for example, Pueblo societies in sort of southern North America. It's been shown in recent studies that there are, well, in simple terms, the early warning signals of loss of stability before repeated collapses of Pueblo societies. That doesn't mean we'll find that signal for all past societal collapses, but if it can be done on, hard to get and archaeological data, for sure, we should be able to do it on contemporary data.
Is there any hope to use what are called integrated assessment models for this sort of work?
Integrated assessment model is a term that covers quite a variety of things. Some of them are just what I would call toy models at the global scale and need to be viewed critically, and currently, in my view, do a very poor job of encapsulating climate tipping point risks, let alone social or ecological tipping point risks. However, other integrated assessment models are much more spatially resolved, or begin to be. I would say, however, that they're very constrained by the underlying assumptions they're making, which is they tend to try to give a policy prescription or advice by assuming an optimization algorithm, which assumes there's only one stable state for society and the economy, and the optimal thing to do is to sort of keep the ball at the bottom of the valley. So the problem with that modeling approach is we now enter a time where either we're going to get forced through these bad social tipping points where that's the wrong model, or we need to trigger these positive social tipping points to a completely different state of the economy, where again, that's the wrong paradigm or the wrong model. So in my humble opinion, the integrated assessment modelers have got some work to do to give us a useful tool for the challenges ahead. But that said, other kinds of models like agent-based models that are being calibrated on actual social data as well as ecological data are a really promising tool for beginning to just understand the dynamics that can happen, whether it's bad tipping or good tipping. So for sure, there's some useful tools out there, modeling tools to bring to the party.
Super. Well, thank you.